Hi, this is Ms. Fitzmaurice, and this video is about force problems that have more than one mass. Okay, so we're going to start out with a really simple problem. Okay, so imagine that you have two blocks, block number 1 and block number 2, and they're connected by a string, and you are pulling them together. Okay, how would you solve this force body diagram? Okay, would you lump the two together and make them into one block? Okay, how would you solve for force of friction? Would you have one for both of them, or would you have individual forces of friction? And most importantly, how would you solve for this tension in the middle? Okay, so what I want you to get out of this video is a couple things. Okay, so from this video, I want you to get what the difference is between internal and external forces. I want you to be able to draw force body diagrams for multiple object systems, and I want you to be able to solve for internal forces. Okay, so before we talk about internal and external forces, we need to define something called a system. Okay, so a system is basically the masses or the objects you care about. Okay, if we think back to my first example, so we had a bunch of blocks sitting on a table, and I'm asking about the force those blocks are being pulled with, the system is probably going to be those blocks and not the table. Okay, if I wanted, I could define the system to either include the left block only or the right block only, but in this case, my system is going to be these two blocks. Okay, that's just the definition of a system. Internal forces are forces between objects in the system. Okay, so if these two blocks are my system, the only force between these two blocks is this tension force. Okay, so this tension between the two blocks, this rope that links them, is internal. External forces are just the opposite. So an external force are forces from objects outside of the system. Okay, so for example, and external forces, I'll make those green. The normal force from the table on both blocks, those will both be external forces. Fg from gravity on each block will be external forces. The force of friction on each block is from the table, so those are external, and the applied force will be external. Okay, so that's the difference between internal and external forces. You pick which objects are in your system. Usually it's pretty obvious. Internal are between the objects, and external are from objects that are not in your system. Alright, so just like with one object problems, when we have two object problems, we usually solve them by drawing a force body diagram and using Newton's second law. Okay, and this may seem kind of weird, but you group the two things together to draw your force body diagram. Okay, and you only include the external forces. Okay, so if you're drawing a force body diagram of the system, you're only including external forces. This between them doesn't matter. Okay, so let's look at this situation and see what forces are acting. Okay, I usually, if I have a system of two things, I will draw the forces onto the objects and then put them onto the force body diagram later. Okay, so I have, in this situation, I have FA acting to the right. It's already there. Okay, I have MG on the first block, so I have FG, I'm going to call this FG2, and I have another FG1. Okay, gravity is pulling down on both blocks. Friction is also affecting both blocks, so I have FF, I'm going to say this is FF1 and FF2, and then both of them are experiencing a normal force, so FN1 and FN2. Okay, and this may seem kind of weird, but we're going to put all of these forces onto one dot. So I have FA to the right. Okay, downwards I have both, and you're going to draw these as separate arrows, both FG2 and FG1, because gravity is pulling down on both of them. To the left, I have two friction forces. I have FF1 and FF2. And then upwards, I have two normal forces, FN1 and FN2. By the way, these little 1s and 2s, they just correspond to the masses of the blocks. Now, if I was writing out my Newton's second law is exactly the same, except that we put a little SYS after the force and pretty much after everything. So it's the total force on the system is equal to the mass of the system times the acceleration of the system. Okay, and so in this case, the mass of our system is going to be M1 plus M2, and I'm just going to leave that as A. Okay, and this is going to be true in X and Y. So in the X direction, I have, and I'm going to draw a little line, I have FA minus FF1 minus FF2, because those are to the left, equals M1 plus M2 times A. Up and down, I have sigma F system Y, because it's the up and down forces on the system, is equal to the mass of the system times acceleration of the system. Okay, what that means is that up and down I have Fn1 plus Fn2 minus Fg1 minus Fg2 equals M1 plus M2 combined times A. Okay, and if I had numbers, I could fill in things for FNs and FFs, but I'm not going to do that for right now. Okay, basically I just took all my forces, put them onto one dot, and the key thing about the equations is that you have two different masses. Alright, so the next question is, what if you wanted to find the internal force? Okay, so say I wanted to know this tension right here. The answer is, to find the internal force, you can't draw a force body diagram of your whole system. you have to choose one of the masses, okay, one of the masses being affected by that force. In this case, I'm going to choose M1, and you have to use that by itself. So you draw an individual object force body diagram. Okay, and what I've really done is I've redefined my system so that M1 is now the whole of my system, and this tension is going to be an external force. Okay, so I'm going to draw my force body diagram. If we are only focusing on M1, we know that gravity's going down. Okay, we have Fn going up, we have Ff going to the side, and some kind of tension going to the right. Say we knew that acceleration was 3 meters per second. We can write out, just like normal, our Newton's second law. Sigma F equals max, sigma Fx equals max, and sigma Fy equals may. Now the question is, which m do I use? Do I use m1 or m1 plus m2? And the answer is, since we now made m1 our system, we're only going to use m1. Okay, so side to side we have t minus ff equals max, and up and down we have fn minus fg, because that's up minus down, equals may. In this case we know that's 0. Okay, now if we had some numbers, like if we knew the acceleration, if we know mu, and we knew the mass, we could solve for the tension. Alright, now I want you to find page 14 of your Unit 3 packet, and you're going to try one of these problems. Okay, you have 3 different masses, and you can assume no friction for any of them. Okay, and you are trying to find the acceleration and the tension in each of the cables. Okay, so spend 5 minutes trying to solve this problem, and then come back for the answers. Okay, so now that you've tried this problem for 5 minutes, 10 minutes, okay, we're going to do this together. So we have 3 blocks. We have 1 kg, and I'm just going to write 1 kg, 2 kg, and 3 kg, and we have 18 newtons. Okay, so we had T1, T2, and T3. Now, if I want to draw a force body diagram of the system, because the first thing I want to find is acceleration, I have to think of my external forces. In this case, we have gravity for each one, so Fg1, Fg2, and Fg3. And then upwards we have Fn1, Fn2, and Fn3. And then we have 18 newtons to the side. Okay, so I'm going to put all of those on my force body diagram. It's going to look a little crowded, but that's okay. So that's just Fg1, Fg2, and Fg3. Upwards, I'm going to have all 3 of them. Fn1, Fn2, and Fn3. Somehow it's not letting me write Fn2. Okay, and then we have 18 to the side. hopefully, looking at this picture, you can realize that only the side-to-side force matters to the movement because there's no friction. Okay, so we're going to write out sigma Fx equals max. Okay, and there's a little system under all of these. So we want to know acceleration of the system. Okay, we have right minus left, so that's 18 minus 0 is equal to the total mass, and our total mass is 1 plus 2 plus 3 times acceleration. Okay, 1 plus 2 plus 3 is 6, and so we can solve for A. A is equal to 3 meters per second squared. Okay, now we want to know T1, T2, and T3. I'm going to solve for T1 first. And in solving for T1, I'm only going to worry about the 1 kilogram mass. Okay, so I'm going to draw my force body diagram. I have T1 is now an external force, Fn, and Fg. Okay, and if I want to know what T1 is, I can use sigma Fx equals max. I know that the only sidewise force on my 1 kilogram mass is T1, so I have T1 minus 0, because it's right minus left, is equal to the mass, which is 1 kilogram, times 3. So I know that T1 is equal to 3 newtons. Okay, if I want to know T2, I'm going to look at my 2 kilogram object. Okay, so I'm going to draw a force body diagram. I have Fn, or Fn2, Fg2, and then I have T2 and T1. I know that in the x direction, sigma Fx is equal to max. For my 2 kilogram object, of course my mass is 2, and I have an acceleration of 3, because these are all accelerating together. Now, my forces are going to be T2 minus T1. So I end up with T2 minus, I know T1 is 3, is equal to 6, and T2 has to be equal to 9 newtons. I can repeat this process to find T3, so I'm going to go to a different page, but hopefully you have this all written down. And for the 3 kilogram object, I have T3, T2, Fn, and Fg. Okay, so to reiterate, at this point I'm only looking at this 3 kilogram object, and I can write out sigma Fx equals max. I know that this is my 3 kilogram object, that acceleration is equal to 3, and I know that I have T3 minus T2 is 3 times 3. I know that T2 is 9 newtons from when I solved for it before. That has to be equal to, or this makes T3 equal to 18 newtons total. Okay, so what we did is, to find acceleration, we used everything together. Okay, we drew one god-awful force body diagram. And then to find the internal forces, we looked at one mass at a time. So hopefully this has been helpful. The next thing we're going to do is we're going to start talking about pulleys and how to deal with pulleys when you have force body diagrams.